All right, so now we move on to lesson 14, and that's net forces in the vertical plane. And this is actually the complement lesson to lesson 13, which was net forces in the horizontal plane. Because as we move forward, what we're eventually going to do is combine the vertical and the horizontal into problems. But for now, we want to be using them as more segmented lessons of first we dealt with the horizontal, and you did that quite successfully. And then now we want to move on to lesson 14 and talk about how we think about these things in terms of the vertical plane, what type of forces are in the vertical plane, and how these problems are solved. Now, in my opinion, these problems are quite straightforward and a little bit more straightforward than even the horizontal, and you'll see why in just a second here. So let's start off with the vertical forces here, and we're going to deal with our first situation, which is what if we have some sort of ball hanging by a rope, and this is our given setup here. So the ball is attached by a string or some sort of chain or some sort of thing that's holding or suspending this object in the air. Well, we actually have two forces that act on this object. One, which is the tension force, and this is new to us, so we definitely want to highlight this in our note. We have the tension force holding up the ball, or the ball is being suspended by that tension force. And then we have the force of gravity, which we've dealt with a ton of times before. So this is our Fg. And if we expanded the definition, we could say that Fg equals mg, like we're going to do throughout the lesson today, but we'll get there when we do it. So the nice thing about the vertical plane is that we only have the two forces acting on it. If the ball was swinging side to side, you could say there's some sort of applied, maybe left or right, and then maybe some air resistance there. But just like we've done in physics 20 throughout the whole year, we're going to ignore air resistance, and we're also going to ignore the fact that we're not going to say that the object is either pushed left or right. We're just purely talking about it in the up and down direction with this. Now, if this is the situation for a ball that's being held up by a string with tension, or string, whatever it might be, chain, rope, whatever it might be, we're going to say that the net force follows the following formula. So in the box here, what I want you to write here is that the F net, or the net force, is equal to the tension force, or the upwards force, plus the force due to gravity. Now, of this ball or of this given object, we know that the Fg isn't going to change because, well, unless the gravity changes and we're on a different planet, then I guess it changes. But if we're on Earth and we're close to the surface, we know that our gravitation isn't going to change, or our gravity value. We know that our mass isn't going to change because mass is just matter composition. So Fg actually remains consistent. It's the Ft that might be changing, which will determine how the object will move either up or down. And we'll see that in just a moment here. Now, something we're going to assume throughout the lesson today is the following. We're going to assume that gravity is negative 9.81, and it's because it's going in the downwards direction. Remember, negatives attached to these things, if we're being precise with these, it's all directional. They're vector quantities, right? So if you have some sort of directional vector quantity, you know that this is going to be either positive or negative, depending on if it goes left, down, up, right. It will have a certain sign. We can think about forces as negative or positive, just as we had always done in the previous lessons. But in today's lessons, what we were going to do is kind of derive where that comes from. Of we can actually just apply the g as the negative component, making the force negative. But we'll see what that looks like throughout the first couple problems here. So let's actually deal with our first in-class problem here. A rope is attached to a 50-kilogram mass. What is the tension force required to accelerate the mass upwards at positive 2.0? Now, as soon as you see accelerate, what I want you to write is highlight that there, and then be like, oh, this is second law. And second law actually implies something very specific about what we're going to do. It means that the net force is not equal to zero. Because if the net force was equal to zero, we would have the first law. So we have some sort of force imbalance that is caused by this acceleration. Or the acceleration is a result of the imbalance force. I should maybe phrase it that way. Now, what we're going to do is we're going to draw a free body diagram, which I highly recommend. I'm going to draw the ball, I'm going to draw the string, and then what I'm going to do off to the side here is I'm going to make an index of positive and negative, because I always like to have the index in there just to make sure that we can understand where the positive and negative is coming from when we assign vector quantities. Now, in this, if it's accelerating upwards, the one thing you should be questioning right away is, what does that mean about the force imbalance? Which force is going to be greater, the tension or the Fg? Well, in this case, if it's accelerating positive 2.0, that means it's accelerating in the upwards direction. And if it accelerates in the upwards direction, what I'm going to do is I'm going to make the red line representing the tension greater than the Fg, which is in the downwards direction or the negative direction here. There we go. So let's actually label these in here. This is going to be our Ft. This is going to be our Fg. And I'm even going to call it Fg equals mg. And I'm going to put my vector tails above both of the symbols I should, aka the gravity and the Fg. Perfect. Okay, now we have our index, we have a free body diagram, fantastic. What we're going to do is we're going to put this all together in terms of an F net statement. So here's what it's going to look like. we're going to say that our Fnet, or the net force, is equal to, we have Ft, which is the tension force, plus Fg. And of course, you never want to forget your vector tails on here because we want to make sure that we're indicating that these are vector quantities or they're directional. What we're going to then do is say, okay, well, I'm solving for Ft, so I'm going to subtract away Fg from both sides. So this goes minus Fg, minus Fg. There we go. Then in my next line, I'm going to have Ft isolated on its own is equal to the net force. And then this is going to be minus Fg. Now, of course, the vector tails are still there, so we haven't assigned directionality or any sort of sign to these. We have to be very particular about this. So now, this is going to be equal to the Fnet, which is always expands to mass times acceleration, minus, in brackets, what I'm going to do is put mass times the gravity, or mg, because Fg equals mg. There we go. Now, here's where we start plugging in the numbers here. We know that it was a 50 kilogram object, so I'm going to write 50.0 kgs multiplied by the acceleration, which was positive 2.0. This is the acceleration it's experiencing vertically, not necessarily the gravity, but the actual acceleration of the object itself. And then I'm going to go minus over here. We're going to put our mass again, which is 50.0 kilograms. And here's where the negative turns the whole force negative. The gravity is negative 9.81 because gravity acts in the downwards direction. What did we denote downwards? It was the Fg, or the Fg direction. So when we talk about this force being negative, and we could even put a little blue indicator here, when we talk about the force being negative, what causes this thing to eventually be negative? It's the positive multiplied by the negative here, which is going to equal a negative here. So this is what makes that force negative. It's that we have this g that is some sort of vector quantity and we assign a sign to it. Now, if you don't want to put negative 9.1 and rather you would just put a negative in front of the whole term and then flip it, it will give you the same answer. But I would just say, like, if we're thinking about these things in terms of like really appropriately assigning the signs in the correct positions, we would associate it with the g because the g is a vector quantity. Gravity is directional. Upwards, downwards, most likely downwards if we're talking about gravitation, and downwards towards a specific object. Now, this is where we summarize the final answer. We say, therefore, the Ft, or the tension force required to accelerate this object upwards, is positive 590 point, and I believe in my calculator I'm getting 5, which to 3 significant digits is going to give us positive 591 newtons. There we go. So this would be our answer for the tension required to accelerate the object upwards. Perfect. And then it should align to the idea that if Ft is going the upwards direction, if we don't get a positive value and we're getting a negative, something's off here. We might want to double check our numbers and double check our signs here, but this looks good. All right, let's try one more example of this. So we're looking at a rope that has some sort of mass, the same mass as before. What is the tension force required to lift the mass upwards at a constant speed? Oh, this one's a good one. Because as soon as you see constant or uniform speed, this implies a different law. In fact, this implies first law, or Newton's first law of motion, which says that the Fnet is equal to 0. There is a balance in the forces, so therefore we say that our net force is 0. Now, we're going to break this apart in the same way. Before we create our Fnet statement, what we always want to do is create a free body diagram. I would highly recommend that. So I'm going to put a ball and a string, or whatever this is, this mass attached to the rope. And then what we're going to do is put our index just like we did before. So we're going to have a positive index, we're going to have a negative index. Great. Okay, now, if I know that the Fnet is 0, what this actually implies, and if it's traveling at a constant speed, is that both the Ft and the Fg are of equal magnitude. So I'm going to try and make sure that these are as equal as possible. And I know those arrows kind of ended up tilted, so I'm just going to draw it off to the side here. There we go. There's 1, there's 2. Perfect. And hopefully these are as balanced as possible. If not, in your notes, make sure that they're as balanced as they can be. So you have Fg, which is equal to Ft, because we want these to be balanced. Fg is equal to mass times gravity, so I'm even going to put that piece in there. Excellent. So now we have our index, we have our forces that are balanced because it's at a constant uniform speed, meaning the forces are balanced. We have an Fnet of 0. Now what I'm going to do is plug this in and treat this as the first piece here. What we may need to do here is, when I look at this problem, I just want to analyze this and be like, okay, well, if I know that I have the first law, then the Fnet is going to be the following. So we're going to say Fnet, or net force, is equal to Ft, tension force, plus the Fg, and I always make sure to put my vector symbols above these. We know that the net force is 0 in first law, or that there's balance, so I know Ft plus Fg must equal to 0, meaning they're equal in opposites. meaning when I expand this even further, Ft is equal to the negative Fg. And again, I haven't assigned any signs yet. All I've done was I subtracted the Fg, so I'm even going to do that algebraic step here. I subtracted the Fg from both sides here. When you subtract Fg from both sides, you get Ft equals the negative Fg with the vector symbol. And then what I'm going to do is to make sure that this shows that it's the positive value, we get negative times a negative force, or negative times the m with the g that would end up being negative. So I'm even going to put that in the bracket here. That means that Ft, or the tension force required, is equal to the positive mg here. There we go. So you can think about it as these are equal and opposites. The Ft just has to be the positive version of the gravity, which would be the negative version. And then if you look at these two, I don't really I don't care about this derivation of saying like, okay, take your Fg and then show that it equals the positive version when you actually do it algebraically like this. I'm more concerned that do you get that logic that under the first law of motion, the forces have to be equal but opposite direction. If you can get that, great, which is shown by this step here. Now, when I actually plug in the values here, let's just double check what we have. We have a mass, we have a constant speed, and we know the gravity, so that's all irrelevant. All I need to put is therefore Ft is equal to the mass, which is 50 kilograms, multiplied by the gravity, which we've already taken care of the sign. As you can see, that g, we dropped its vector symbol. We dropped the vector symbol, which is above here, by putting the negative right here. So because we see this negative, it came from the fact that we knew gravity was going to be negative. I can just write this as 9.81 meters per second squared. There we go. Therefore, when I do the math on this, my tension force required in order to keep this at a constant motion would be 491, and it's going to be positive. So I just want to make sure I put the plus there, 491. Now, if you're one of those types of people that were like, oh, why can't we just put 491 up? You could. So in fact, you know what I'm going to do is just put that right off to the side. 491 newtons in the upwards direction. If you wanted to also put it that way, I would be totally fine with that. Both of those would be completely correct. Now, what does this say about Fg? Simply put, Fg, if we wanted to expand upon our answer, we could say this, and I'll just even put this in brackets below. Fg would be equal to negative 491. So if you wanted to like show the comparable, or 491 down, because we know that the forces are equal and opposite, I know it didn't ask for this in the problem, but if you just wanted to put that below, just so that you can conceptually see that they're equal and opposite, and that's what causes that net force to be zero, great, fantastic. Okay, whoa, skipping around a little bit. Okay, now let's go on to the third problem here. Another example that deals with the same similar concept, but maybe just asking for something slightly different. A rope is attached to a 50 kilogram mass. If the upwards force is 280 newtons is applied on this rope, what is the resulting acceleration of the mass? Now, as soon as I see acceleration, I love to highlight that and then put second law right away, because we know that acceleration is due to this second law. And so I'm going to say that my F net is not equal to zero. I think it's always really important to classify not only the law, but then what that means in terms of the F net, because then it helps you narrow down like, am I just going to make it zero right away? Am I going to make it some sort of statement where I need my mass times acceleration? In this case, we do need mass times acceleration. We know they gave us a mass, they gave us some sort of applied force or some sort of tension force here. And so I'm going to call this the Ft, because they said a force is applied in the upwards direction on this rope. What is the resulting acceleration on the mass? Well, let's actually just figure this out here. So we're going to put our free body diagram just like we always do. So off to this margin here, I'm going to put a ball, and I'm going to make that a little bit better. There we go. Perfect. I'm going to attach a string to it. I'm going to put my index, which is very important. So we have a positive and a negative. What I'm going to do from here is then I'm going to put the different forces at play. The only thing that's tough about this problem is that there's no indication on whether the force is going to cause some sort, or the net force is going to cause it to accelerate downwards or upwards. So in an odd way, what I would do right away is I would fill in the diagram, just currently making them equal. Now, that might seem a little counterintuitive because you're like, well, isn't this where it's in balance? Yes, but what we want to do is we want to just put these in for now. And then at the end of the problem, what we can always do is just go back and then edit the length of these. But what I want to be really careful with is as I start this problem, if I know that I'm going to be doing some sort of F net statement and solving for acceleration, I want to figure out what forces are at play. And so it's sometimes helpful to have them just visually, and then we can always edit the diagram. So what we're going to do is we're going to create our F net statement. F net is equal to the combination of these two forces, so Ft plus Fg. And of course, I'm always going to put my vector tails on these, just like I've said before. I'm going to make that one a little neater. There we go. Now I'm going to expand this out because we're solving for the acceleration of this mass, or which way it accelerates. It's going to be mass times acceleration is equal to ft plus, and then what I'm going to do is put mg right here. Excellent. Now, if I want to solve this for the acceleration, I have to divide both sides by the mass here. So I'm going to divide the left by this. I'm going to divide the right by mass. Now, what this is going to do is that it's going to cancel the mass from the left, and then I'm going to have on the right-hand side this ft plus mg over mass. Now, if you do this, if you realize you have mass and mass, please do not cancel them like this. Because in mathematics, we always look at this and say, if it's not attached to all three of these terms, you cannot cancel the mass off this. So because I don't see mass here, I can't just simply be like, oh, these are gone and continue forward. No, that is a totally wrong algebraic step. Please do not do that. So I'm going to take these blue hashes back. We're going to look at this and say, okay, therefore the acceleration is equal to the ft, in this case, which was positive 280. They said it was applied force in the upwards direction of 280, plus our mass times gravity, which is 50.0 kilograms, multiplied by, here's where the negative 9.81 comes in, because we know that the gravity is directional, and then divided by the mass, which was 50 kilograms. There we go. Okay, here's what it's going to give us for an acceleration. Right away, I'm looking at this numerator here and being like 280 plus a negative 50 times 9.81. This looks like it's going to be something that ends up being negative because the numerator looks to be negative. In fact, when we actually get the answer, we get negative 4.21 meters per second squared. We could also rephrase this as the following: 4.21 meters per second squared in the downwards direction, if we wanted to put it that way. So I'm going to put this as down. There we go. And I'm going to highlight this here. Now, if we end up getting this negative 4.21 meters per second squared, what this means is that the acceleration is going in the downwards direction. And now we got to look at our diagram and think of the following. If I'm given this situation where we originally wrote them out as balanced, just to help us identify what the forces were, we have to edit this and say, now the FG is longer than the FT, or else it wouldn't accelerate in that given direction. And I'm going to make sure I match it to the red here. So I'm going to make this like drastically longer. There we go. So this is going to be our FG. Whoops, there we go. There's going to be our FG, which is equal to our mg. There we go. So this definitely shows a force imbalance where the FG, or the force due to gravity, is larger than the FT, and that force imbalance causes the object to accelerate in the negative direction. So again, if you don't know the acceleration or you don't know the direction of the acceleration, you may have to find it and then edit your free body diagram from there, which is totally fine. Nothing against that. What I would always do, though, is just make sure you draw them out right away so you know your forces at play. Okay. Now, here's where we move on to a different section. So we talked a lot about, in those first three examples, tension and how tension can either cause positive acceleration or negative acceleration. And if you have a certain amount of tension, it can mean you're either lowering the ball or you're raising the ball, or maybe you're lowering or raising the ball at a constant velocity or a constant speed. Those situations all come up, and with dealing with the different Newton laws of motion. Now what we want to talk about is this idea of elevators and apparent weight, or what we're going to learn to call our Fn, the normal to whatever this surface is. Okay, let's break down a couple things, and then we're going to draw some diagrams to emphasize how this actually comes together. So upon entering the elevator, you feel a normal amount of weight, right? You enter the elevator, nothing changes. You're just standing on the platform and you're waiting for things to happen. When you start to accelerate upwards, you end up feeling heavier than you normally would. So you start to feel a sort of weightiness to your comparable normal, where like normally if you're just standing in the elevator, you're not feeling any different. As soon as it starts to accelerate upwards, you feel a little heavier. When you're traveling uniformly, like let's say you're in the middle of your journey from floor 1 to floor 10, so you're about floor 5 or 6, you would feel normal, because if you're traveling at a constant speed, it's not like you're accelerating in any given direction. You would have some sort of force balance there. So, your normal weight would feel exactly what you're experiencing, or your normal weight would be what you're actually experiencing in this case. Now, when you're slowing down as you reach the top, you start to feel lighter on your feet, or less weight on your feet. So I could even put, like in this case, you feel less weight on your feet for that. But you could also say you feel lighter on your feet, whatever you want to put there. Less would make this sentence a little more comparable and make it make sense here. Now, what we're going to do is we're going to expand upon this because I think, we could say these things or verbally all we wanted, where we accelerate upwards, we feel heavier. We travel uniform, we go normal. When we're slowing down, we feel less. But we want to show it visually and how this actually applies together. So what I'm going to do is I'm going to open up another page here and I'm going to draw the three following boxes. And I highly recommend you do this as well. So I'm going to draw one box representing the first situation, two box representing that second situation, and then a third box representing the third situation. Okay, now, and I'll even number these here. I'll be like, this is situation 1, situation 2, and situation 3. Excellent. Okay, here's what we're going to do. In the first situation, they told us that we have some sort of person that's getting in an elevator, and I guess that applies to all three. When you get in an elevator, we need to realize that our FG does not change. So what I want you to do on all three of these diagrams before we've even began is I want you to draw the FGs all the same length. And I want you to even indicate that these are your FGs. So this is my FG, this is my FG, and this is my FG. Now you're probably thinking, like, how does the FG not change in all three of these situations? Isn't this dynamics? Isn't things happening with the forces? No, because remember, your mass doesn't change. Your matter composition isn't just rapidly changing as you're in the elevator. And on top of that, we're thinking that the gravity, as long as you're close to Earth, it's not going to start changing. So unless we go to a different planet or we're way off the surface of Earth, then it changes. But we're going to assume that this person's on an elevator that's in Earth and we're experiencing all these different things. So the FG will remain the same. What does change, though, is depending on the situation, it's going to change our apparent weight, or Fn. So what I'm going to do is, in the first situation, they said we accelerate upwards. I want you to put a dotted line like this, arrow upwards, and say, this is our acceleration. Now, this is really common in physics to use dotted lines to represent velocities or accelerations, and they're given directions when it comes to net force diagrams or free body diagrams. So we accelerate upwards. Well, based on our physics knowledge to this point, we always said if acceleration is going in a certain direction, it means the net force is going in that direction, meaning in this first situation, the reason we feel heavier is because as we accelerate upwards, we feel or we experience a normal force that is greater than our regular weight, which is Fg. And so the force imbalance there is represented by the acceleration direction, but not only that, it's our idea that we're experiencing a force that is greater than our regular weight, and thus we feel heavier. Now, in the second situation, we're traveling constantly, just upwards at a regular uniform speed. So if we travel at a constant uniform speed, it actually means these two forces are completely balanced, perfect with each other. So the Fn, or your normal weight, is, and I shouldn't say Fn in terms of normal weight, your apparent weight, which is Fn, is equal to your actual weight, or your regular weight, Fg. The last situation was the following. What if instead of accelerating upwards, what if we're reaching the top and we start to accelerate in the downwards direction, or we're slowing down? Well, what this means is that if I know that the acceleration is going in the downwards direction or towards the Fg, it means the Fg must be greater than the Fn. So I'm just going to put a tiny Fn here representing this, and then I'm going to indicate that this is our Fn, making sure to label it. There we go. And so whatever the direction of the acceleration, remember, we've always dealt with this in dynamics to this point, acceleration and the direction of acceleration determines the overall direction of the net force. Because by definition, a net force is something that has some sort of accelerated motion in a given direction, or an F net that's not equal to 0. Okay, so hopefully with these diagrams, this will provide a little bit more of a clarity around the physics principles we've talked about and how apparent weight comes into the picture. If you need to on any given assessment, or they asked you on a multiple choice, I would just draw out this little elevator box and draw what's happening and be like, hey, if acceleration is going up or down, or if there's no acceleration, what does that mean in terms of the forces? And then resort back to your knowledge of this unit. Now, I'm going to flip back to here, and I just want to highlight one more thing here. So it's that line right below here, and it says the following. The weight you are feeling is not gravity, but your apparent weight. If it is the force of the floor pushing on your feet. So Fn, just like we've talked about before, is always that perpendicular force. It's the 90 degree to the surface you're on. So when they say it's the force of the floor pushing up on your feet push down on the floor with your regular weight. And then what happens is that based on what's happening in the surrounding, or based on what's happening with the given situation around you, it's going to cause you to have some sort of different normal force, or contact force, as we would call it back in the previous section. Okay, now here's where we go into our F net. Our F net is just the following. So we say that instead of it being F net equals Ft plus Fg, now the only thing that we change is we make this F net, or the net force, is equal to, instead of Ft, now it's just Fn plus Fg. So the Fg and the Fnet are going to stay where they are and stay in place, but the Fn is what changes here. And Fn is still a positive force, just like Ft was, because both of those go in the upwards direction. It's just different meaning, different problem. Okay, let's try an example where we actually deal with this, because the next situation comes right after this, but I want to truncate these into tension, normal, and then potentially thrust after that. Okay, now let's take a look at the example here in the following. If you weigh 706 newtons when an elevator is stopped, what is your apparent weight if you're in an elevator that is accelerating downwards at a rate of 1.65 meters per second squared? Well, right away, here's a big thing to highlight right here. Accelerating. Again, just like we've done before, we're going to make this second law. If we know that this is second law, it means our F net, or the net force, is not equal to 0. There we go, because we have a force imbalance. The other really tricky thing here, and the thing that you're going to get really good at throughout this year, is if they give you this key information. If you weigh 706 when the elevator is stopped, they're giving you your FG. This is just another way of saying, oh, here's your FG. Can you use that to help you solve the problem? And of course, yes, we can, because that's a part of our net force. It's going to be a definite helpful piece of information. One thing I kind of want to derive right away is, in this problem, they didn't give us any mass. And we know how critical mass is for these problems. So when they do this sort of situation and they say, oh, you weigh this, and when the elevator stopped, they're trying to hide the mass from you in a kind of a sneaky way. Here's how they do it. When you look at this problem, you would say that, okay, well, if Fg is equal to 706, Fg is equal to mass times gravity by definition, or the multiplication of mass times gravity. If I isolate this for mass, it's going to give me mass is equal to Fg divided by G. And now if this is the case, I'm going to put in the following. This would be negative 706, which is the amount of newtons of force in the downwards direction, right? Because it's your Fg, it's in the downwards direction. So I'm going to put negative because it's a vector quantity. I'm going to put negative 9.81 because that's our gravity as we're close to the surface of Earth. There we go. Perfect. And if I do the math here, I end up getting that the mass of this object is equal to 71 point, and I believe it is 97 when rounded to a second decimal place. I think you want to keep as many decimal places as you can, but this is our mass here. Okay, here's the really important thing to notice with this. Now that we have our mass, now that we have an FG, we can solve the rest of the problem from here. We've actually figured out all the critical information, and we've uncovered that hidden piece of information that comes from when they say you weigh a certain amount. They're just hiding the mass from you, but they're also giving you one of the forces. So it's kind of it's a nice thing for that, is they're giving you one thing, but they're kind of masking another. Now, we're going to draw out our free body diagram. So off to the side here, I just recommend you draw in some sort of elevator box like this. Now, off to the side of that, I'm going to put a positive and a negative representing the up and the downwards direction, because you always want to make sure you have that. We could draw like our friendly little person in here that's riding the elevator here. And now what we want to do is indicate what's happening with the forces. If they say in the problem, we are accelerating at a downwards rate, well, if we're accelerating downwards, it means that the Fg is greater than the Fn. So what I'm going to do is, in the elevator, Fg, and then my Fn is just going to be smaller in the upwards direction. I'm going to make sure that's an arrow. There we go. So this is my Fn. This is my Fg, which is equal to mg. Excellent. There we go. And if you're wondering why I always put the mg, it's just so that by definition you recognize that the force due to gravity could also be solved when you have a mass and your gravity for any given situation. Okay, so, and then I'll even put a dot in the middle of these forces, because that might look like they might be balanced depending on where you put the center line. So there you go. That's our forces. Now, right away, what would you say about this person? They would most likely feel lighter than they normally do, because their Fg is their actual weight, their Fn is their apparent weight, or the weight they're experiencing. When you're accelerating downwards in an elevator, it means you actually feel lighter on your feet. Now, we're going to put together our Fnet statement from here, because we have all the critical info we need. Fnet is equal to the Fn plus the Fg. There we go. We want to solve for our apparent weight in this case. So our Fn, when we isolate it, we're going to subtract away the Fg from both sides. So this is going to give us Fnet minus Fg. And I got to make sure I have my vector symbols on these, because I haven't assigned direction yet. Now, zooming into this, I'm going to make this equal to mass times acceleration minus, I'm going to actually keep this as FG. And you're probably thinking like, why wouldn't we expand out the definition and make it mg? Well, they actually gave us the weight already. Remember, in the beginning of the problem, they said if you weigh this amount, 706, they've given us the actual newtons already. So I'm not going to plug in those newtons, or I'm not going to plug in the mass times gravity. Rather, I'm just going to do it as FG. We could do it the other way, but that's totally optional. Now, when it comes to the mass times acceleration, you're seeing why we needed that mass from earlier. The mass is directly used in the FNet, so that's why it's critical. If we didn't have the FNet and it was a balanced force, maybe we don't need the mass, but in this case we do. Now, I'm going to say that Fnet, or the normal force, the contact force, or your apparent weight, I'm not going to use normal, but I'm going to use the contact force, or your apparent weight, is equal to the mass of this object, which is our 71.96 or 71.97, according to the calculations, multiplied by the acceleration, which if it's going downwards at 1.65, it's negative. So this is negative 1.65 meters per second squared. And then this is going to be minus, in brackets, negative 706 newtons. Now, again, you're like, wait, why is it negative 706? Because we're going in the downwards direction. So the force would have to be negative. Remember, there's operational negatives, which is what these are. And then there's directional negatives, which is what this and this are. So anything that's in the brackets is directional. Anything that is out of the brackets is non-directional. Okay, so now we're going to put this together and say, therefore, our Fn, or the apparent weight we're experiencing, is equal to, and from my math, I end up getting positive 587 newtons. So this would be the answer you should be getting here. Now, again, you could consider this 587 newtons in the upwards direction. That would be equally as okay as well. So I may even put that in here. So 587 newtons, and then we could say up. That would be okay too. Now, what I want you to retroactively look at in this problem is the following. So when we zoom out of this problem, what we want to immediately compare to is our FG greater than our Fn in the end? And it's true. If you compare FG, it's 706. If you compare our Fn, it's 587. Which one is greater? It is definitely the 706. So according to our logic and the Newton's laws of motion, this aligns to what we would expect to see, where the Fg would be greater than the Fn in the given situation where we have something that is accelerating downwards. And even to put this on here too, because we did this in our other diagrams, what I'm going to do is just put down an arrow like this and say that our acceleration is going downwards. That may be something you want to add as kind of like a last little step there, just to indicate that if your acceleration goes in a direction, that force must be greater. All right, now the next example relies on the fact that we have to create a definition of what is happening with rockets. So rockets is our third and final example for vertical forces, or vertical plane forces that are imbalanced with each other, or balanced or imbalanced depending on the given situation. So in the vertical plane, we've now dealt with tension, we've dealt with elevators and apparent weights. Now we want to deal with rockets and thrust and see how this changes things, if it does change things at all, very slightly. Now, when we look at this problem here, what we want to do is say the following, or when we look at the definitions that are being established here, a rocket that is being traveled upwards, there's two forces acting on it. The first force is going to be thrust. Thrust is that upwards force that causes the rocket to get lifted off of the ground, and we derive this by saying it is the force TH. There we go. Now, the other force that's acting on it is gravity. So you have some sort of upwards force, you have some sort of downwards force in Fg that relies on gravity and mass. Now, by definition, thrust must overcome or work against the gravity in order to get the object into the air or into the sky. And so if there's not enough thrust and gravity is greater, we don't get the object getting off the ground. If thrust is able to be enough force to overcome gravity, then the object will accelerate upwards, or the rocket accelerates upwards. And very familiar, this is not going to look much different. Our net force, or the Fnet, is going to be equal to our FTH. And I know my THs in class sometimes look a little rough, so I'm going to make sure I space those out. Sometimes I tend to like blend them together. FTH plus our FG. There we go. And just like we've seen with the other net forces, the only substitution was with the positive force, because we're classifying that positive force in different ways depending on the different scenarios. Now, I'm going to flip over and we're going to use this information of we need a certain amount of thrust to overcome a certain amount of gravity, which therefore would cause the rocket to accelerate upwards, and we're going to use this new FNet statement here. Okay, last problem. We have this certain rocket that has mass of 1.2 times 10 to the 3 kilograms, and it produces a certain amount of thrust, aka 3,000 newtons or of this, or 3.00 times 10 to the 4. So, and this would actually be a little more. So what I'm going to do is I'm going to say this is our FTH right away. And I highly recommend you arrow to this right away. If they give you thrust, we want to make sure we have this. Now, they also give us the mass, so I'm going to put M right above here. And they ask us, if there's a certain mass for a rocket and it has that amount of thrust in newtons, what is the speed of the rocket this amount of time after the launch? Interesting. Okay, if they start bringing up kinematic concepts, you know that there's going to be a connection between the two. Now, right away, what I would want you to be thinking is, what is the connection between dynamics to kinematics? Because there was a very specific one, and a lot of you in class would say, oh, it's time. But in this case, not really. No, time was the connector when it came to projectile motion, which was purely in kinematics. But if I want to go backwards and forwards between the two, what I have to realize is that the connection between kinematics to dynamics and dynamics to kinematics is the acceleration. If I can figure out acceleration, I can then open the doors to tons of kinematic situations that would come from this. So let's draw our free body diagram right away. I'm going to draw this rocket that looks like this. I know, not super perfect. It's all good. Now, I'm going to draw my index, and I'm going to be consistent here. I'm going to draw it all in black here. So this is going to be positive is upwards, negative is downwards. And if I want this rocket to be lifted out of the air and eventually be in the air at some point, we know that the acceleration would have to follow that the net force is greater in the vertical direction upwards than the vertical direction downwards. So my force thrust, or my F thrust, must be greater than my Fg. There we go, Fg, which is equal to mass times gravity, which is mg. Excellent. Okay. Now, we're going to break this into a couple components here. The first component is going to be to say, we need some sort of FNet statement. So what I'm going to do is, for part number one, we're going to draw out our FNet statement, where FNet is equal to, and this is going to be FTH plus Fg. Excellent, there we go. Now, what we're going to do is we're going to make a substitution here. So we're going to make it where our FNet is equal to, and then from here, I'm going to make this in terms of, I'm thinking, do I expand this out? I think I can, where I can just expand out my FNet to mass times acceleration is equal to FTH plus, and then I'm going to make this mass times gravity. There we go, excellent. And then what I'm going to do from here is I'm going to divide both sides by the mass. And again, it would be a very dangerous thing to do to cancel out your masses here, because they have to be included on all three. If they're not included on all three, please do not just be like, oh, mass and mass, I see two of them. No, it has to be on all three. In 20-1, when I teach math 20-1, I always say, do not cancel those, because it's not in everything. It's the all or nothing principle. Either you see it here, here, and here, or you can't just see it as these two and cancel it. Doesn't work that way. You circle them all and you say, is it on all three? If it's not, don't cancel it. Great. Okay. Now what I'm going to do is say acceleration is equal to the FTH, which in this case was 3.00 times 10 to the 4 newtons. And this is in the positive direction. I'm going to include in brackets, plus the mass, which I'm going to make sure I get this accurate, was 1.2 times 10 to the 3. And this was kgs, of course. Your gravity is equal to negative 9.81, because we're talking about the force of gravity going downwards, or the overall acceleration of gravity going downwards, and then thus the force of gravity going in the downwards direction. And then we're going to divide this by the mass again, which was that 1.2 times 10 to the 3. There we go. So therefore, our acceleration is equal to, now right away, before I even touch my calculator, I should be thinking what this is going to give me. Hopefully you should be thinking in the back of your mind, it must be giving me a positive acceleration. Otherwise, if I got a non-positive acceleration, it would mean that this is actually going through the ground, which I don't want. The acceleration has to be going into the air or in the positive direction. So I'm going to get a final answer of the following, positive 15.19. And this is meters per second squared. You could also consider this the upwards direction. Now, I'm going to highlight this. Not saying it's the final answer, but I'm highlighting it in terms of this is our connecting point between kinematics and dynamics. If I can get the acceleration, I've now opened up an infinite situation of different problems that I could solve with this based on the fact that acceleration can now be passed into like so many equations. And depending on that information, I now can analyze this in terms of a kinematics problem in many, many different ways. So our problem specifically asked for what was the speed after the launch or after 45 seconds of launch. So what we're going to do is we're going to list out some variables here. Here's what we have. In terms of kinematics, we have VI, VF, change in time, and acceleration. So I'm going to list all of those nice together. I'm going to make sure I have my vector symbols on these. My VI is going to be 0 meters per second because at initial point of launch, it starts on the ground. VF is our question mark. After 45 seconds, we're trying to figure out what this is. So I'm going to put 45 seconds here. And then in terms of our acceleration, it's positive 15.19 meters per second squared. Now, which equation does this lead us to in kinematics? You should be thinking, oh, it's the basic acceleration equation. It's VF minus VI divided by the change in time. There we go. Now, if I'm solving for VF, I'm going to start by multiplying up time. So this is going to be multiplied by time, multiplied by time. This is going to give me the following. I have A delta T is equal to VF minus VI. Now, the beautiful thing about this equation is the way it is we know that VI is 0. Our initial velocity is 0. So if we really wanted to, we could even just cancel that out right away. Therefore, your VF is equal to acceleration times time. Let's actually formalize that here. VF is equal to the acceleration, which is positive 15.19 meters per second squared, multiplied by the 45 seconds, or 45.0 seconds. And therefore, I get a final velocity, or a VF, which is equal to, and just to make sure I get this right, it's going to be in the upwards direction, or it's going to be going into the sky upwards, but let's write out the answer rounded to the nearest significant digit, which would be 684, and I'm going to make sure I put positive. 684, this is meters per second, because we're talking about a speed or a velocity. The other acceptable answer here would be 684 meters per second in the upwards direction. So if you just said up like this, that would be totally fine. I would think that this is great. There we go. Now, this should make sense that we get a positive velocity that has been accelerated because the acceleration is causing the object to gain velocity in that upwards direction, the acceleration being in the up direction. And we now can confirm back to this and say, well, all our math is aligning to a force thrust being greater than the force due to gravity. And that's because we're getting a final velocity that goes from 0 to something in the hundreds, and the acceleration follows in that direction in the net force. Now, again, when we zoom out of this whole problem and we're looking at it from a macro level like this, as we are, you want to make sure you have your free body diagram. You want to make sure that if there's any mention of kinematic concepts like time, velocities, displacements, you want to make sure that you're saying, what is that connecting piece? That connecting piece I need is the acceleration. Most likely, how do I get that? Through the net force, I can get my acceleration. And once you have your acceleration, just like we did in kinematics, the unit before, we listed our variables, we list out our variables, choose an appropriate formula, and then solve for the variable. So of all the ones we did in class today, this one would be the hardest one to do just because it now establishes that connection between kinematics and dynamics in terms of the vertical plane, which we're going to do more of throughout the year. But here's where we see a kind of a first situation of that in terms of how it happens in the vertical plane. We did do this in the horizontal plane before. All right, here's where you want to get your practice problems done. I highly recommend you do practice problems for these. You want to master both the horizontal direction and the vertical before we get to lesson 15, where we start to mash them together and put these concepts all together in terms of both horizontal and vertical plane acting together.